Hi everyone, we will learn differential equations in this session. Differential equation involves derivatives or differential coefficients. Okay, and for example, form differential equation of simple harmonic motion given by x is equal to a times cos nt plus alpha. So we are supposed to eliminate the constants a and alpha. Okay. So now differentiating this, we get dx by dt is equal to minus na sin nt plus alpha. Differentiating it once again, d square x by dt square is equal to minus n square a cos nt plus alpha, and this is a, this is x. So differentiating it twice, we get minus n square x. Thus d square x by dt square plus n square x is equal to 0. So we can say that this is the solution of this differential equation, right? Next is order and degree. Order is the order of highest derivative appearing in it, and degree of highest derivative occurring in it. After the equation has been expressed in a form free from radical, express in a form free from radicals and fractions. For example, let us consider one plus dy by dx whole square raised to the power minus 5 by 3 is equal to a times d square y by dx square. So after removing radical, we can rewrite this as 1 plus dy by dx square whole square raised to the power minus 5 is equal to a cube and d square y by dx square whole cube. Yes. So now, since the highest derivative is d square y by dx square, so highest order derivative is 2, hence the order is 2, and degree, so degree of the highest derivative, so highest derivative is d square y by dx square, so degree of this highest derivative is 3. So this equation is of order 2 and degree 3. So order 2 and degree 3. Similarly, let us see one more example. 1 plus dy by dx whole square whole to the power 3 by 2 divided by d square y by dx square is equal to c. So this can be written as 1 plus dy by dx whole square, okay, and let us take this on the right hand side, so multiply this with c d square y by dx square, right, and then 3 and take 2 power 2 on the right hand side, so this will be c square and d square y by dx square का whole square. Now since the highest derivative occurring in this is 2 again, so order is, this equation is of the order 2 and the degree of the highest derivative, that is d square y by dx square, degree of this is 2 again, so this equation is of order 2 and degree both as 2. Okay, let us see some few more examples. So if you have d square x by dt square plus a square x is equal to 0, then obviously this is order is 2 because highest derivative appearing in this equation is 2 and degree of this is 1, so order is 2 and degree 1. Okay, so this way you can say whether what is the order, and you can find out the order and the degree of a differential equation. Okay, so next is solution of a differential equation. Solution of a differential equation. Okay, so as we saw, we can say that in the equation of SHM, while finding the differential equation of simple harmonic motion, we can say that x is equal to a cos nt plus alpha is the solution of this differential equation. Okay, so we have a general solution. Okay, so if the number of arbitrary constant is equal to the order of the differential equation. Then it is called the general solution of the differential equation. Okay. And next is particular solution. When the arbitrary constant takes some unique value then that solution becomes the particular solution of the equation, right? So by using boundary conditions, the particular solution of a differential equation can be obtained, right? Okay, so next is equations of the first order and first degree. So first is variable separable form. Variable separable method. So if in an equation it is possible to collect all functions of x and dx on one side, collect all functions of x and dx on one side, and all the functions of y and dy on the other side, so if this is possible in an equation, then the variables are said to be separable. Thus the general form of the equation is fy dy is equal to phi of x dx. So now integrating both sides, we get f of y dy is equal to integral phi x dx plus c. So this is the solution. Okay. So for example, let us solve dy by dx is equal to e raised to the power x plus y plus x square e raised to the power y. So this can be written as e x and ey and ex plus x square. Okay, so that means given equation is this dy by dx is equal to e raised to the power y whole multiplied by ex plus x square. Now taking dx on the other side and e raised to the power y on the left side, so e raised to the power minus y and ex plus x square dx. Now integrating both sides, we have minus e raised to the power minus y is equal to e raised to the power x plus x cubed by 3 plus constant. Okay, so now this can be written as minus 3 e raised to the power minus y is equal to 3ex plus 3x plus x cube and plus 3c, so some other constant. So this is the required solution of the differential equation. So again, let us take another example. Solve dy by dx is equal to x plus y plus 1 whole square, and you are given initial value problem. So y of 0 is equal to 0. So this equation is given with an initial condition. So this is initial value problem, right? It is used to determine the value of the arbitrary constant in the general solution. Okay, we just saw, right? Okay, now let us put x plus y plus 1 is equal to t. Then we get dy by dx and dx by dx plus 1 is equal to dt by dx. So differentiating this with respect to x, now dt by dx is equal to dy by dx is equal to dt by dx minus 1 . Yes. So now the given equation becomes dt by dx minus 1 is equal to t square or dt by dx is equal to 1 plus t square. So now this has been reduced to the variable separable form. Okay. So now we can easily solve by taking dx on the right hand side and 1 plus t square to the left hand side. So dt by 1 plus t square is equal to dx, and integrating both sides we get tan inverse t is equal to x plus c. And now let us replace t by x plus y plus 1. So we have tan inverse of x plus y plus 1 is equal to x plus c. And we know, and from the initial condition we have, if x is 0, y is equal to 0. So if x is 0, y is 0. So when x is equal to 0 and y is equal to 0, we have tan inverse 1 is equal to c. That means tan c is equal to 1. That means c is equal to 45 or pi by 4. Hence the solution is x plus y plus 1 is equal to tan x plus pi by 4. Right? So we saw that equations of the form dy by dx, okay, and function of x and y, like we can conclude that equation of the form dy by dx is equal to f of a x plus by plus c can be reduced to variable separable form by putting ax plus by plus c is equal to t, right? Next is homogeneous equation. Homogeneous equation. Any function that can be expressed fxy that can be expressed in the form of x raised to the power n f of y by x. So then it is called homogeneous function. Of degree n in x and y. To solve homogeneous equation, first step is put y is equal to vx, then differentiate with respect to x to get v plus x dy by dx. Now use variable separable method. Separate the variables v and x and then integrate. For example, solve v square minus x square dx minus 2xy dy is equal to 0. So given equation can be written as dy by dx is equal to y square, this is y square minus x square by 2xy so we can write this as y by x square minus 1 by 2 okay. So this is a homogeneous function in x and y of degree 1, right? So now put y is equal to vx, then dy by dx is equal to v plus x dv by dx. So now the equation becomes dy by dx becomes v plus x dv by dx and v square x square minus x square. So x square, take x square common, vx square minus 1 by 2 vx square, x square gets cancelled, so we have v square minus 1 by 2v. Okay, now take this v to the right hand side. So x dv by dx is equal to v square minus 1 by 2v minus v, that is minus of v square minus 1 by 2 times v. Now we can separate the variables. So 2v by minus 1 plus v square dv is equal to minus of dx by x. Now integrating both sides, 2v dv by 1 plus v square is equal to minus of dx by x plus some constant. So this is nothing but log of 1 plus v square. So put 1 plus v square as t, then 2v dv is equal to dt, so dt by t, and then log t, and then again replace t by 1 plus v square. So we have solved such kind of integration before. So this is minus log x plus c. Okay, and we can take this minus on the power of x. So log of 1 by x plus, so this constant we can write this as some log of some another constant, right? Now we can take log 1 plus v square is equal to log c dash by x. Now taking anti-log on both sides, we have 1 plus v square is equal to c dash by x. Again replacing v by y by x. 1 plus y by x whole square is equal to c dash by x. That means x square plus y square is equal to c times x, or x minus c by 2 whole square plus y square is equal to c square by 4. So that means this general solution represents a family of circles with center on x-axis at family of circles with center at c by 2 comma 0 and radius c by 2, right? Okay, next is linear equations of first order, right? So first of all let us see how we can differentiate between linear and non-linear differential equation, right? For example, linear equation and non-linear equation. Let us see some example. So for linear, like for example dy by dx plus 3y is equal to 2. So this is a linear first order differential equation, okay? And for non-linear we can have y dy by dx is equal to 5. So this is the non-linear equation. Similarly, this is also if the equation contains the term such as x square d square y by dx square. Do not confuse. This is again a linear differential equation. Okay. Similarly, for non-linear, if we have the power of derivative, degree of derivative, then this is non-linear, or we can have dy by dx plus root under y. This is again non-linear. Okay. So now let us learn how to solve such kind of equation. So Leibnitz linear equation. The standard form of linear equation of the first order is dy by dx plus py is equal to q, where p and q are the functions of x. P and q are functions of x. So to solve such equations, multiply both sides by integrating factor. So integrating factor or IF is e raised to the power integral p times dx. So this factor is multiplied on both on. I will show you how we multiply both sides by e raised to the power integral p dx. So dy by dx e raised to the power integral p dx plus y e raised to the power integral p dx times p is equal to q e raised to the power integral p dx. Notice that this is nothing but derivative of y e raised to the power integral p dx. So if you consider y as u and this as v, so this is in the u into v form. So derivative of u into v is u dv plus v du. Okay. So u dv plus v du, right? So this is equal to q times e integral p dx. Now integrating both sides. Integrating both sides, we get y e integral p dx is equal to integral q e raised to the power integral p dx plus c as the required solution. Let us understand this with an example. Solve x plus 1 dy by dx minus y e raised to the power 3x and x plus 1 whole square. Okay, dividing x plus 1 throughout the given equation becomes dy by dx is equal to minus y by x plus 1 this is equal to, okay, so minus y by x plus 1 is equal to e raised to the power 3x and x plus 1. So this is now a Leibniz equation. Okay. So standard form of linear equation of the first order. Okay. So this is Leibniz linear equation. Now where P is minus 1 by x plus 1 and this is P and this is Q. Okay. Then integral P dx will be minus 1 by x plus 1 integral 1 by x plus 1 dx, that is minus of log x plus 1, or you can take this minus here. So that means we have 1 by log of 1 by x plus 1, right? And now integrating factor if is equal to e raised to the power integral p dx. So e raised to the power log of x plus 1 minus 1 is 1 by x plus 1. Yes. Now the solution of this required differential equation is integral e raised to the power 3x x plus 1 q into if integrating factor, that is 1 by x plus 1 dx plus c. So x plus 1 gets cancelled. So we have 1 by 3 e raised to the power 3x plus c and on the left hand side y times if, that is y by 1 plus x so this is the required solution. Y is equal to, so this is the required solution of the given equation, right? Now let us understand Bernoulli's equation. Bernoulli's equation. So for earlier we saw that a differential equation is said to be linear if the dependent variable, okay, and its differential coefficients occur only in the first degree and not multiplied together. Okay, so that was our first order linear equation. And then Bernoulli's equation, if we have the equation of the form dy by dx plus py is equal to q y raised to the power n, where p and q are the functions of x, p and q are the functions of x. So this form can be reduced to the Leibniz linear form and this form is called Bernoulli's equation. So to solve this divide both sides by y raised to the power n, then this equation becomes y power minus n dy by dx plus p y 1 minus n and q. Okay, now let us put y raised to the power 1 minus n as z, so that so that 1 minus n y raised to the power minus n dy by dx is equal to dz by x. Now this equation, okay, now the first equation, original equation becomes, this equation becomes 1 by 1 minus n dz by dx plus pz is equal to q. Then dz by dx is equal to p times 1 minus n z is equal to q times 1 minus n. Right? So which is a Leibniz linear differential equation in Z, and now it can be solved easily. This is plus here. Clear? So let us understand this with an example. Okay, solve x dy by dx plus y is equal to x cube and y raised to the power 6. We have to remove this y term from the right hand side. So we will divide y, okay, x y raised to the power 6. So dividing throughout by x y raised to the power 6. We will get y raised to the power minus 5 by x is equal to x square. Okay, so why we chose to divide x raised to the power x y raised to the power 6 because we need this, we have to make this in the form of Leibniz linear equation. So in Leibniz linear equation we have just dy by dx, we need just this term, we don't, this should not be here, and we have, and this sort should not be here, since there should be p and q in the form, in the, as the arbitrary functions of x. So if we remove y raised to the power 6, so this will become function of x, which is q, and then if we take x here in the, and we can remove this x here from here and take the in the denominator, then this will again become a function of x as 1 by x, and this will be removed. So now we will have a Leibniz linear form. Now put y raised to the power minus 5 as z, so that minus 5y raised to the power minus 6 dy differentiating both sides will be equal to dz by dx. So now this equation becomes minus 1 by 5 dz by dx minus y minus x dy by dx is equal to minus 1 by 5 dz by dx, and this is z, so z by x and is equal to x square. And now since this is a constant, we can take dz by dx, we can multiply by minus 5 on the both side, we will get minus 5 by 5z by x is equal to minus 5x square. So now we have got a Leibniz linear form in z. So now integrating factor is e raised to the power p dx. So integral p dx. So p is minus 5 by x. So minus 5 by x and dx. Which is e raised to the power minus 5 log x, or this can be written as e raised to the power log x raised to the power minus 5 log x raised to the power minus 5, which is equal to x raised to the power minus 5. So now solution is z into integrating factor is equal to integral q minus 5x square into integrating factor dx plus c, which gives z into x raised to the power minus 5 is equal to integral minus 5x square into x raised to the power minus 5 dx plus c. Now we know that z is y raised to the power minus 5. So replace z by y raised to the power minus 5 and x raised to the power minus 5 is equal to, this is 5x raised to the power minus 3, and if you integrate this you will get x raised to the power minus 2 by minus 2 and plus some constant. So now we have got the required solution, or we can simplify this further. So by dividing it throughout by this y raised to the power minus 5 into x raised to the power minus 5, then this will be equal to 1, and so this is 2.5 into y raised to the power 5 and x raised to the power 5 plus c and y raised to the power 5 and x raised to the power 5. So this is the required solution for the given differential equation. Okay, now let us go to the homogeneous form That is, we can, if we have the equation of the form dy by dx is equal to ax plus by plus c divided by a dash x plus b dash y plus c dash. So this can be reduced to the homogeneous form. So case 1, when a by a dash is not equal to b by b dash, then put x as x plus small h and y as y plus small k, where h and k are constants. Then dx will be equal to dx also dy will be equal to d of y. Now this equation will become dy by dx is equal to a x plus by plus ah plus bk plus c divided by a dash x plus b dash y plus a dash h plus b dash k plus c dash. To make this equation homogeneous, we need values of h and k so that ah plus bk plus c becomes 0 and a dash h plus b dash k plus c dash is equal to 0. So solve these two equations for h and k. Now this equation becomes homogeneous. So this becomes dy by dx is equal to ax plus by by a dash x plus b dash y, which is homogeneous in capital X and capital Y and can be solved by putting y is equal to vx, and then we can proceed the same way we did earlier. Now the second case is when a by a dash is equal to b by b dash. Okay. So now in this case, let us say a by a dash is equal to b by b dash. Let us assume this is equal to 1 by m. Say 1 by m. Okay. Now a dash is equal to am and b dash is equal to bm. Now put the values dy by dx is equal to ax plus by plus c by m ax plus by plus c dash. Now put ax plus by as t so that differentiating this with respect to x, we will have a plus b dy by dx is equal to dt by dx, or dy by dx is equal to 1 by b dt by dx minus a. Right? Now this is equal to, let us equate this equation and this equation. So we have dy by by dx is equal to 1 by b dt by dx minus a is equal to t plus c by mt plus c dash. Okay. Now dt by dx is equal to a plus bt plus bc by mt plus c dash. Okay. So again this is equal to am plus b times t plus ac dash, okay, whole divided by ac dash plus bc obviously, and mt plus c dash in the denominator, so that the variables are now separable. So we can use variable separable method, right? Now putting t is equal to ax plus by back in the value, we will get the required solution, right? Now next is exact equations. Okay, exact differential equations. So differential equation of the form m xy dx plus n x comma y dy is equal to 0 is said to be exact, is said to be exact if its left hand member is the exact differential of some function u m dx plus n dy is equal to du. Okay, so next is the necessary and sufficient condition for the differential equation to be exact is del m by del y is equal to del n by del x. Okay. Necessary and sufficient condition to be exact. Okay, clear? So next is method of solution. So the solution of m dx plus n dy is equal to 0. Solution of is integral m dx assuming y as constant plus integral terms of n not containing x dy is equal to c, provided del m by del y is equal to del n by del x. Yes. So let us understand this with an example. Solve y square e raised to the power xy square plus 4x cube dx plus 2xy e raised to the power xy square minus 3y square dy is equal to 0. So here m is equal to y square e raised to the power xy square plus 4x cube and n is equal to 2xy e raised to the power xy square minus 3y square. So del m by del y is equal to 2y then e raised to the power xy square plus now y square times e raised to the power xy square into 2xy, and this with respect to y is 0. Now differentiating, taking partial derivative of n with respect to x by taking y as constant. So you will get the same. Differentiating this with respect to x will be 0 and differentiating this with respect to x will be 2y e raised to the power xy square plus 2xy e raised to the power xy square into y square. So they are the same. That means equation is exact. Equation is exact and its solution will be integral m dx y constant plus terms of n not containing x so y square e raised to the power y square x plus 4 times x cube dx and terms of n not containing x, that is so minus 3y square, omit this, so minus 3y square dy is equal to c, or so assume y as constant, so this will be equal to e raised to the power xy square and y square by y square, which will get cancelled, plus x power 4 by 4, so 4 will get cancelled, and here so minus 3y raised to the power 3 by 3, then 3 will get cancelled, so y cube. So this is the required solution. Okay. Sometimes a differential equation which is not exact can be made so on multiplication by a suitable integrating factor, and such equation can be reduced to an exact equation, and then we know how to handle exact equations, right? So first is integrating factor by inspection. Okay, so if we can spot x dy plus y dx in equation, then this can be replaced by d of xy. Similarly, if we can spot y dx minus x dy by y square, then this is nothing but d of x by y, right? And then we can integrate, then we will get the solution. Okay, let us understand this with an example. Say we have y 2xy plus 1 dx minus x dy is equal to 0. Now 2xy square dx plus y dx minus x dy is equal to 0. And if we divide by y square on both sides, we will get 2x dx plus 2x dx plus dx y dx minus x dy by y square. So this is nothing but d of x by y. So this is 2x dx plus d of x by y is equal to 0. Now we can integrate. So integrating, we have x square by 2 will get cancelled. So x square plus x by y is equal to c. So this is the required solution. Let us take one more example. Solve y 2xy plus e raised to the power x dx is equal to a raised to the power x dy. Right? Now expand. So 2xy square plus y e raised to the power x dx is equal to e raised to the power x dy. Okay. So now if we again divide by y square, y square and y square. So we will get 2x dx plus yex dx minus ex dy y square. And this is nothing but d of e raised to the power x by y. Yes, u by v form. This is in the u by v form. So v du minus u dv by v square. Now integrate on both sides. So this is x square plus this is d of e power x by y, okay, is equal to 0. This is x square by 2 will get cancelled, plus e raised to the power x by y is equal to constant. So which is the required solution? Okay. Similarly, if you may find x dy minus y dx by x square plus y square, then this will be equal to d of tan inverse y by x. Okay. So this way you can make a equation reduced to exact equation, and then we can proceed. So next is integrating factor for of a homogeneous equation. If m dx plus n dy is equal to 0, be a homogeneous equation in x and y, then integrating factor is 1 by mx plus ny. Right? Let us understand this with an example. So solve x square y minus 2xy square dx minus x cube minus 3x square y dy is equal to 0. The equation is homogeneous in x and y. How? So if you divide x cube, so let us divide x cube, multiply and divide x cube. So x square y by x cube minus 2xy square by x cube dx minus x cube 1 minus 3x square y by x cube dy. So this is x cube and y by x minus 2y square by x square dx minus x cube. We can take the whole x cube common, minus 1 minus 3y by x dy. Yes, now this is homogeneous because the function can be expressed in the form of x cube function of y by x. So this is a homogeneous function in degree 3 in x and y. Hence homogeneous of degree 3. Right? So now let us solve this. We have found out that this is a homogeneous function. Now integrating factor is 1 by mx plus ny. Okay, m is x square y minus 2xy square times x minus x cube minus 3x square y times y this is equal to x cube y minus x cube y will get cancelled, and minus 2x square y square plus 3x square y square, that is 1 by x square y square. Now multiplying throughout by 1 by x square y square, the equation will become, this equation will become multiplying throughout by 1 by x square y square, which is an integrating factor, So 1 by y minus 2 by x dx minus x by y squared minus 3 by y dy is equal to 0. So which is exact? Now the solution is, we know the solution of exact equation is integral m dx keeping y as constant plus integrating terms of n not containing terms n not containing x dy is equal to 0. See now, so m dx, this is m, so y is constant, so this will be minus 2 log x and x by y, so x by y minus 2 log x. Okay, and for this terms of n not containing x, so omit this and just take minus 3 by y, so this will be plus 3 log y, plus 3 log y is equal to c, right? Okay, then third is integrating factor for an equation of the type f1xy times y dy, dx, y dx plus f2xy x dy is equal to 0. So if the equation is of this type, then this is m and this is n. So this is m dx plus n dy is equal to 0. Then 1 by integrating factor will be equal to integrating factor will be equal to 1 by mx minus ny, right? Okay, so and then we can proceed as usual. So let us take one example. Solve 1 plus xy y dx plus 1 minus x 1 minus xy x dy. Okay, so here this is two different functions in xy. So m is 1 plus xy times y and n is 1 minus xy times x. Now integrating factor will be 1 by m times x minus n times y is equal to 1 by 1 plus xy times xy minus 1 minus xy times xy. So which is xy plus x square y square minus xy. So xy get cancelled, xy and minus xy, then plus x square y square, then This is equal to 2 times x square y square. Now multiplying throughout by the integrating factor we just got. One by 2 times x square y square. It becomes 1 by 2 times x square y plus 1 by 2 times x dx plus 1 by 2 times xy square minus 1 times 2y dy is equal to 0. So now this is an exact equation. Again here the solution will be integral y, taking y as constant, m times dx, integrate m times m dx and integrate n terms of n not containing x with respect to y. Let us directly put the values. So this is with respect to x, taking y as constant, right? Then this will be 1 by 2x square y plus 1 by 2x dx plus minus 1 by 2y dy is equal to c. Because this term contains x, so we are omitting this. So we are okay, we left that. Next, integrating this 1 by 2y minus 1 by x and plus 1 by 2 log of x, and for this minus 1 by 2 log of y is equal to c. So this is the required solution. Now we can further simplify this since we have log here. So if you take half common, then it will be log of x minus y, so log of x by y. So this is nothing but minus 1 by 2 times xy and plus half log of x minus log y, which can be written as log of x by y. Yes, and then we can remove this 2 from here and we can take this on the right hand side 2c, which can be replaced by another constant c dash. Okay, so this is the required solution. Now next type is, in the equation m dx plus n dy, obviously which is not exact, if del m by del y minus del n by del x whole divided by n is a function of x, say fx is a function of x only, say fx, then integrating factor is e in power integral f of x dx. And if del m by del y minus del n by del x, I again wrote that only, So if del n by del x minus del m by del y whole divided by m is a function of y only, say f of y, then integrating factor is e raised to the power integral f of y dy. Okay. Let us take one example. Solve xy square minus e raised to the power 1 by x cube 1 by x cube dx minus x square y dy is equal to 0. Okay. So here m is xy square minus of e raised to the power 1 by x cube and n is minus x square y. So let us find del m by del y minus del n by del x, and this is equal to okay, 2xy and minus del n by del x, so which will be minus of 2xy, then 2xy plus 2xy, and then so this is 4 times xy. Then if we divide by m, then we will not get any function of either function of x only or function of y only. So if we divide by n, so we can get function of x only, right? Let us see. So let us divide by n by minus x square y. So this will be equal to 4 times xy by minus x square y is equal to minus 4 times 4 by x. Okay. Now we have got this as a function of x only. So which is fx. Then integrating factor if is equal to e power fx dx, integral fx dx, so which is equal to e power minus 4 log x, and if we can take this minus 4 on the power of x, so this will be equal to x power minus 4. Right, now multiplying throughout by x power minus 4, we have okay. So x power minus 4, we will have y square by x cube minus 1 by x power 4 e raised to the power 1 by x cube dx minus y by x square dy is equal to 0, which is an exact equation. Now the solution is integral y square by x cube minus 1 by x raised to the power 4 e power minus x cube, sorry, x power minus q dx plus, since there is only one term of n containing x, so we will take 0 here. See, now integrating this, we will have y square x power minus 3 plus 1, that is minus 2 by minus 2 plus, so integrating this you will get 1 by 3 e power x power minus 3 okay is equal to C. So this is the solution, required solution. Okay, now next is equation of the first order and higher degree. Equation of first order and higher degree. Okay, so we denote dy by dx as P. Let us see this with an example. Solve dy by dx minus dx by dy is equal to x by y minus y by x. So given equation is, if we put p at the p in the place of dy by dx, so p minus 1 by p is equal to x by y minus y by x. So which is p square minus 1 is equal to p times x by y minus y by x, and so we can, this is a quadratic equation in p square minus p by x by y minus y by x plus 1 is equal to 0. Yes. Okay, this is minus only. So this is a quadratic equation. Though now factorizing, we will get p plus y by x and p minus x by y is equal to 0. Thus we have p, either p plus y by x is equal to 0 and p minus x by y is equal to 0. So from this we have dy by dx is equal to minus y by x, so which is equal to x dy plus y dx is equal to 0, which is d of xy is equal to 0, and integrating we will get xy is equal to c, right? Similarly, this will be dy by dx is equal to x by y. Okay, so this will be equal to y dy minus x dx is equal to 0, so which is y square by 2, integrating we will get y square by 2 minus x square by 2 is equal to 0. So y square minus x square is equal to, this is C. Right? So 2C. So now xy is equal to C and y square minus x square is equal to 2C constitute the required solution, and combining these two into one, the required solution will be xy minus C into y square minus x square minus C dash is equal to 0. Thus the required solution is this. Okay. Okay, let's wind up here. I will share this notes on my Telegram channel. You can find link in the description. We will learn applications of differential equations in the next lecture, and then we will solve problems on differential equation. Keep preparing. Thank you.